Hello everyone, welcome. In this video we're checking out variant 2 of Major 9709, paper 4 mechanics. Let's get started. Question number 1 says a small smooth spheres A and B of equal radii and masses 5 kilograms, 3 kilograms respectively lie on a smooth horizontal plane. Initially B is at rest and QA is moving towards B with a speed of 8.5 meters per second. So we can draw that A is moving towards B, that's stationary. So this is A and this is B, and we can say here we have a mass of 5 kg. However, here we've got a mass of 3 kg. The velocity here equals 0, but here velocity equals to 8.5. We have the spheres, they collide, and after the collision, A continues to move in the same direction, but with quarter the speed of B, meaning A is going to have the same direction, but it's going to have velocity, which is 1/4 the velocity of B. Okay, so he says find the velocity of B after the collision. Well, we know here to use momentum because during collisions momentum is conserved, and so momentum initial equals to momentum final. And so initial momentum, we know momentum is supposed to be mass times velocity, and initially we only had A moving, and therefore there was only A's momentum, and so again mass times velocity of A initial plus mass times velocity of B, obviously mass of A initial will equal to the mass times velocity of A final, and A obviously plus the mass times velocity of B final. Now here mass times velocity of A is just 5 times 8.5 plus mass times B is 3 times the velocity, which is 0, which must equal to the mass of A 5, but its speed we said already was 1/4 the velocity of B plus mass times velocity of B final, which is mass over here is 3, and then velocity B final. We're trying to find this. So now calculating one side. 5 times 8.5 is 42.5, which must equal to 5/4 plus 3. 5 divided by 4 plus 3 is actually 17/4 V of B. If we divide 42.5 by 17/4, you get V to be 10 meters per second, which means that A is going to have a velocity of 2.5. So let's just keep that down as a note for us. Okay, he says find the loss in the kinetic energy of the system due to the collision. Notice here, when we want to find the loss in kinetic energy in momentum questions, what we do is we get the initial momentum when like we had stage 1 when A was rolling, and then the final momentum at the very end, whatever happened later. Like, we don't care what happens in the middle, we care what happens at the very end. Now in this case, because we only have two things happening, just A moving, then they collide, so it's really easy. We just get the kinetic energy before the energy final. So the initial kinetic energy was equal to what? In general, kinetic energy equals to 1/2 mass times velocity squared. Initially A was moving, so the kinetic energy was just of A, and so it was 1/2 times its mass 5, and its velocity, which was 5, or what was the velocity? It was 8.5 meters per second. 8.5 squared, that's initial velocity, and it's going to turn out to be 180.625 joules. Then the kinetic energy final is going to be the kinetic energy of A and the kinetic energy of B. So it's going to be 5, and then times 2.5 velocity of A, but then here for B we're going to have 3 as the mass and the velocity 10, and that's going to be 0.5 times 5 times 2.5 squared plus 0.5 times 3 times 10 squared, and that is equal to 165.625. Now if you subtract the two, you will get the loss in kinetic energy due to the collision. So we call this collision an inelastic one because kinetic energy was lost. Now it will be negative, but because it's lost, I'm just not going to write the negative sign. Okay, next question. We have resolving of forces, chapter 2. Coplanar forces of magnitude 60 newtons, 20, 16, and 14, as you can see, point in the directions shown in the diagram. Find the magnitude and the direction of the resultant force. Now to find the resultant force, we need to get all the components in the x direction and all the components of the forces in the y direction. So I'm going to get the table over here made, and I'm going to write fx for components in y, and for components in x, components in y, and in the end we're going to add them up and get the resultant using that information. Firstly, let me resolve these on this page over here, and then we're going to have an imaginary y-axis, 20 sine 60. So we know that this angle over here is going to be, 20 is going to have an x component where cosine is going to be there, while the y component is going to have sine. And then 16, again, sine on the y-axis, because the angle here is made with the x-axis. If the angle was made with the y-axis, then we'll put the sine on the x and the cosine on the y. For 16 sine 50, here we're going to have 16 cosine 50. And that's it. So let's go ahead and write down everything here. So we have 60 on the y-axis, and we have negative 20 sine 60, negative 16 sine 50, and we also have here 0 for the component on 60. We have, however, 20 cosine 60, and we have negative 16 cosine 50, and we also have 14, negative 14, but 0 on the y-axis. Adding all these together, you get 10 minus 16 cosine 50 plus minus 14, and that's going to be negative 14.284601. And then for the y component, you get 60 minus 20 sine 60 minus 16 sine 50, and that's going to be 30.42278. Anyway, using this information over here, we can find the resultant in magnitude, but we also need to find the direction, so that's going to be important later. But we just get the components and use the Pythagorean theorem. And then for negative 14.284601 ... squared, and then we just go ahead and calculate these two values. So answer squared plus 33.609, which rounds to 33.6 newtons. Okay, now in regards to direction, we have a negative component on the x-axis, which we can draw a right angle triangle between the tip and tail. Now this is the positive y component, and the resultant is going to be between them, and this is going to be the resultant. Now we want to find this angle over here. Now since we have the components here and the length is not negative, so it's just 14.284 ... we can find the angle using tangent of theta. Let's call the angle theta is equal to 30.422 divided by 14.284 ... and then you can get tangent inverse of this whole thing, and you will get the answer. And so tangent inverse is 64.848, which rounds to 64.8 degrees from the negative x-axis. Okay, so we can write clockwise, this is anti-clockwise, support the specified direction, clockwise from negative x-axis, or in other words, if it's going to be right here, then we can add 180 degrees to it, subtract 180 degrees from it, and we can say 115.2 degrees clockwise from the, so it's this time, no, it's also anti-clockwise from positive x-axis in this case, not negative, like here. Okay. Okay, question 3 says two particles A and B of masses 2.4 and 1.2 kilograms respectively are connected by a light and extensible string which passes over a fixed smooth pulley. A is held at a distance of 2.1 meters above the horizontal line, while B is closer to the ground at 1.5 meters above the plane. The particles hang vertically and are released from rest, and in the subsequent motion, A reaches the plane and does not rebound. However, B does not reach the pulley. Okay, so let me just go ahead and do a quick sketch. We have particle A, which is 2.1 meters above the ground, and particle B. So this is particle A and this is particle B. Particle A happens to be 2.1 meters above the ground. Meanwhile, particle B is going to be only 1.5 meters above the ground. When particle A is going to fall through the distance, B is going to rise a distance of 2.1 above the 1.5. It's already above the ground. Okay, so let's go ahead and see part A. It says, show that the tension on the string before A reaches the plane is 16 newtons and find the magnitude of the acceleration of the particles before A reaches the plane. Now, because we know A is going to be going downwards, then in order for us to find the tension and to find acceleration, the only way to go about solving this question about connected particles is to use Newton's second law of motion. Now, Newton's second law of motion says tension, net forces must equal to mass times acceleration. Now we already know that the net forces on particle A. Let's start with particle A. So particle A is going to have a what's called weight pulling it downwards, which is supposed to be in the case of A24. But then there's also tension in opposite direction and opposing the direction of motion, and that's going to be the thing that we want to find. Then we also have the mass of A, which is 2.4 times the acceleration that we don't know. For particle B, we know it's moving upwards, and therefore its tension minus the 12 newtons of weight, which are opposite the direction of motion, times 1.24 mass times acceleration. We have two equations in terms of tension and acceleration. We can solve them together as simultaneous equations in order to find the values of acceleration and tension, which are exactly what he wants. So if I add these two equations together, I will be able to eliminate tension because it's negative and positive in the two equations, and so they cancel out. Now 24 minus 12 will equal to 3.6 times acceleration. 24 minus 12 is 12. 12 divided by 3.6 is 10 over 3. So acceleration is 10 over 3 meters per second squared. Meters per second squared, yes. Now in regards to the tension, we want to find tension. We could just simply use the second equation if we like. Tension will equal to, any one of the equations will do, but I think this one's okay, so let's use it. 10 over 3 instead of acceleration. Tension will equal to 16 newtons, which is exactly what he wanted. Perfect. Now for part B, it says find the greatest height of B above the plane. This is a frequently repeated connected particle question, and if you want to solve a whole lot of these, you can go back to 2015, or I'm not sure when they introduced it, but when they first introduced the chapter, they were asking lots of questions about connected particles. So this question can be solved by finding out sorry about this. So they're asking for the height that B is above the ground. So how about we just copy the sketch right over here in part B. Now in part B, what happens is that A is now on the ground. Meanwhile, B has risen that distance of 2.1 meters. And so despite it was already 1.5 meters above the ground, now it's another 2.1 meters above the ground. But that's not the final answer. 2.1 plus 1.5, 2.1 plus 1.5 is actually equal to 3.6 meters above the ground, I believe. Yes. Okay, so this whole thing is 3.6 meters. But particle B won't stop at this. Now, if a particle like A hits the ground, they said that A is not going to rebound, and so it lost its energy on contact with the ground. However, particle B still has some kinetic energy that did not lose immediately as the particle A hit the ground. When particle A hits the ground, particle B still has some inertia and still has some kinetic energy, and so it will want to move a little bit more, and then it's going to lose all that kinetic energy, lose that inertia, and it's going to be, it's going to have a velocity of 0, and then return back to that position that it was above the ground when A hit. So we see this sometimes in real life. It's not that far-fetched for you to imagine. Just remember that in connected particles, the particle doesn't stop at where this thing stops, because otherwise he wouldn't ask 3 marks to find the answer to this question, because then the answer would just be 3.6 meters, which was pretty easy to obtain. Anyway, as we have figured, the particle is going to continue moving, and it's going to continue so until it lost all its kinetic energy, so velocity will be equal to 0 at that point. And when it's moving during that second stage, after the A hits the ground, the tension is actually going to equal to 0 in the string, because the string will become slack as soon as the as soon as A hits the ground. So acceleration is actually going to be negative 10, because we're only moving under the effect of gravity, since there's no other force acting. You can see how this now turned into a chapter 1 question, since we are trying to find the displacement and we already have 2 of the uniformly accelerated motion variables. We just need a third one. As I mentioned, we need another one because we can only find one of the variables, like displacement, if we have 3 other variables. And so to find another variable, I think we can find velocity, or initial velocity, because it's the only thing in common between stage 1 and stage 2. And so we can find that pretty simply using the acceleration of the first stage, using the displacement of the first stage. And another thing, I think we also have the initial velocity of the first stage because it starts from rest. So since I already have the acceleration, it was positive 10 over 3 meters per second squared of the initial stage, and I have the initial velocity, since he said it started from rest, and I also know that it's going to rise a distance of 2.1 meters, I can pretty easily find the final velocity of stage 1, which will help me find, which is going to be exactly the initial velocity of stage 2 and hence help me find the displacement. So let's go ahead and do this. The displacement, so what equation am I going to be using? I'm going to be using v squared equals u squared plus 2as. Now v squared is unknown, but 0 plus 2 times 10 over 3 times 2.1 equals to v squared. V will equal to radical 14. Now we can use it right here, so we can say that initial velocity was equal to radical 14, and again use v squared equals u squared plus 2as, but this time to find the displacement. And so instead of velocity you put 0 here, you put radical 14 all of it squared plus 2 times negative 10 for acceleration, and then you can just go ahead and calculate. So it's 14 divided by 20, and that's displacement, which is going to be 0.7 meters. Now we're going to add 0.7 to 3.6, and that's supposed to be the height you are above the ground, which is 4.3 meters above the ground. That's the maximum height that you're going to be reaching. So a quick little recap in case things got messy. Remember that this question contains two stages. The first part is the part where it moves 2.1 meters up when A was still moving with it, after which tension was equal to 0 when A hit the ground, and so it's the new stage when we're moving with a different acceleration. When you move with a different acceleration, you need to use a different equation, because obviously that means that the acceleration is no longer constant, and so you want to consider this a totally different stage. In stage 2, we have final velocity, we have acceleration, but we still need one more thing to find the displacement that it will travel during that stage. So in order to find that final thing, we just use whatever is common between stage 1 and stage 2. Final velocity in stage 1 is actually the only thing in common between the two stages. Stage 1 will have it as final velocity, stage 2 will have it, stage 2 will have it as initial velocity. And so I chose to find it because it's the only thing in common between the two stages. And so we used one of the uniform acceleration motion equations in order to find the final velocity. Then we substituted it here as initial velocity, and we used v squared equals u squared plus 2as to find the displacement, added it to all the distances together to find the maximum height above the ground, which is 4.3. Question number 4 says a particle A moving along a straight horizontal track with a constant speed, and it's given to you, passes a fixed point O. 4 seconds later, however, we have particle B that passes through point O moving along a parallel track in the same direction as A. Particle B has a speed of 20 meters per second when it passes O, and its constant acceleration of 2 meters per second. B comes to rest when it returns to O. Because we have two particles, I prefer that we use a velocity time graph in questions like these, because it's a little bit tricky to keep up with everything that's going on, and these help to prevent a lot of messes. So let's go ahead and do this. Now, particle A is pretty simple. It's just something moving with a constant speed of 8. Particle B, however, starts 4 seconds later. So we can consider this because as 4 over here. This is the velocity time graph. And at time 4, particle B has a speed of 20 meters per second. So it says 20 on the y-axis. And it has a constant deceleration, so it's a negative gradient. And we can see, actually, he said that it comes to rest when it returns to O. So that means it was moving like this away from O, then it comes back to O. And so that means that the velocity also changes direction, and then at a certain point it will have to come to rest, and that's the point it reaches O. And I think, up should be looking symmetrical to down, because the area under should equal to the area above, since here we're going back the same distance, and I think we're going to have instantaneous. I'm not really sure how it's going to come to rest. Since it didn't specify much details, I can just leave it broken. That doesn't really matter right now. Let's see what question letter A says. Find expressions in terms of t for displacement of O from each particle t seconds after B passes through O. Okay, this is very important. He said t seconds after B is passes through O. So we're considering time 4 over here to be our starting point. We're gonna ignore that this guy has been moving for 4 seconds, and we're just gonna pretend that everything started right here. Although we know that A is going to be ahead by a certain distance, which is 8 times 4 all the time. But we're going to consider the time right now to be 0 at this point, and it just moves on forward. 1, 2, 3, 4. Okay, so the displacement of particle A is supposed to be velocity times time, because it's moving at a constant speed. But you're also going to add to it, this area over here, which is 32, which is the displacement it covered while B was not moving. Okay, and so the displacement of A is going to be 8t plus 32. Another way of saying this is just like saying, okay, it's supposed to be 8 for velocity, however time is going to be time plus an extra 4 seconds that we were moving when B was not moving. However, for displacement of B, it's going to be, we're going to use a uniform acceleration uniform acceleration equation, which is going to include initial velocity, time, and acceleration, because we have all these three things. And so we just go ut plus half at squared, and so ut is going to be displacement of b is equal to 20t plus half of -2, because it's acceleration, t squared, and so displacement of b equals 20t minus t squared, and that's it. Okay. For letter B, he says find the values of t when the particles are the same distance from O, meaning we're going to make the two equations equal to one another. So 8t plus 32 equals to time, what was it again? 20t minus time squared, and so we just, we get a quadratic equation that we want to solve on our calculator. And so 1 minus 12 and 32 is going to be a time of 8 seconds and a time of 4 seconds. So he's asked for the values of t when the particles are the same distance. These are the values of t. Now the reason there are two values of t is because we know this over here, b is going, away from O and then back towards O. And so they happen to be, the same distance away from O. Okay, part C says that on a given x-axis, sketch the displacement time graph for both particles for values of t from 0 to 20. So considering this is a displacement time graph, it will be different to my velocity time graph. But because we already have the equations, we found them before, of displacement in terms of time, this should be far easier. 8t plus 32 and displacement equals to, pretty sure it was 20t minus t squared. So you could see how this one is going to look like. It's going to be a straight line, but for the other one it's going to be a parabola because it's a quadratic equation. So it's important that when we sketch parabolas to find a couple of things, meaning being the x-intercepts, the y-intercept, the turning point, obviously. So let's start first with the straight line, then come back here. And an important thing here is that these two curves are supposed to intersect at times 4 and 8. So let's go ahead and see how we can sketch this. First, we're going to have a y-intercept for this one at 32. I don't have an accurate measure, but I'm going to assume it's right here. We can also find, for example, that at time 10, what the displacement was equal to. And I think that's going to be 112. So let's say 112 is approximately right here. So connecting between these two dots, almost. Well, anyway, for this one, however, we're going to have the x-intercept at x equals 20 and at x equals 0, which you're going to find on your calculator, but you also should know because he said that it starts from rest and that it comes back to rest at time equals 20 in part I. Another thing that you want to know is that it's supposed to have a turning point at x equals minus b over 2a, and minus, in this case, b minus 20 over 2 into minus 1, so that's at x equals 10. So at x equals 10, this the displacement is going to actually be equal to 100, right? Yes, 10 squared is 100, and so it's going to be 100 meters. And so at 10, right here at 100, we're going to have the turning point, but we're also supposed to have these x-intercepts, and this is how the graph, okay, sorry about that. But anyway, you could see there are two intersection points, and they're supposed to be at time equals 4, at time equals 8, and that's it. Now here we have a block of mass 12 kilograms on a plane which is inclined at 24 degrees to the horizontal. A light string makes an angle 36 degrees above the line of the great slope which is attached to the block. The tension in the string is 65 newtons. The coefficient of friction between the block and the plane is mu. The block is limiting equilibrium and is on the point of sliding up the plane. So if the block is on the point of sliding up the plane, that means the friction is going to be right here. Friction is also equal to mu r. And we also know that here we're going to have weight, but the weight is going to be resolved, so it's going to have sine of 24 with it. On the other hand, we're going to have here weight cosine of 24. Remember, weight is the only thing that takes sine on the x-axis and cosine on the y-axis. Here we're going to have the normal force, and we're also going to have the resolving of the 65 Newton force. So 65 sine, so here you can see sine is on the y-axis. However, cosine is going to be on the x-axis. Meanwhile, weight is going to be the opposite case in an inclined plane. Now we're going to go ahead and try to find mu, given that we are limiting equilibrium, meaning this side equals to this side. The forces on the left are equal to forces on the right, and the forces on up are equal to the forces down. And so we're going to have 65 cosine 36, which must equal to the weight. Weight is equal to 120 sine 24, and then mu. However, we need to find r. R is going to equal to weight, or 120 cosine 24 minus 65 sine 36, and this again is coming from the idea of up being equal to down. 65 cosine 36 must equal to 120 sine 24 plus mu, not 140, 24, mu times 120 cosine 24 minus 65 sine 36, and that is, we're going to solve the calculator. So 65 cosine 36 is 52 point whatever, and then minus 120 sine 24 is going to be 3.0. Okay, that's 3.777, and we're gonna also what's it called, and there's parentheses here, that's gonna equal to mu into 120 cosine of 24 minus 65 sine of 36. Now you can go ahead and divide by this on either side. 65 sine 36, and then you can also divide by this right here, 65 sine 36. So if we get this and divide by 120 cosine 24 minus 65 sine 36, you would get mu equal to 0.05289. We can round this to 0.0529. Question number 6. A car of mass 100 kilograms is moving up a hill inclined at sine inverse equal to 0.12, sine inverse of 0.12 to the horizontal. The initial speed of the car is given to you after 12 seconds. However, the car has traveled 150 meters up the hill and has a speed of 16 meters per second. The engine of the car is working at a constant rate of 24 kilowatts, which is the power of the engine. He says find the work done against resistive forces during the 12 seconds. Okay, so to find the work done against resistive forces, we're going to first, let's sketch this quickly. So we have 900 kilograms over here, so 9,000 newtons, or 900 kilograms. We're going to have initial speed u equals 11, and the final speed of 16 in a time of 12 seconds. And I have power, and I know that power equals to the work done by the engine divided by time. So if I find the work done by the engine, if I want to find the work done by the engine, I can just go ahead and use power times time. The reason I'm finding the work done by the engine is because I know work done by driving force equals to change in kinetic energy plus change in gravitational potential energy plus the work done by resistance. And this is known as the work energy principle. So using power times time, again, I need to first convert power to watts, so that's going to be 24,000 watts. And so you're going to say work equals to 24,000 times 10 seconds, no, times 12 seconds, and so 24,000 times 12 is equal to 288,000 joules of work done. Okay, so work. So this is going to equal to change in kinetic energy, which is equal to 1/2 times the mass of 900 times final velocity squared minus initial velocity squared, and not the whole thing squared, each velocity squared on its own. 16 squared minus 12 squared, 11 squared, minus 11 squared. And then you're going to add this to the change in gravitational potential energy, which is going to be, since he's moved 150 meters up the hill, 150. Meanwhile, the vertical height is going to be, well, we can use the right angle triangle, we can use sine, cosine, and tangent, and sine in this case is equal to, opposite over hypotenuse. Well, because we're looking for the opposite, we'll just multiply by the hypotenuse, and so hypotenuse sine theta equals to the opposite. Now notice here, sine inverse is equal to 0.12, which means that sine theta in general equals to 0.12. So instead of sine theta, I can just go 0.12, okay, and that's equal to the opposite side. And I have the hypotenuse of 150, so the vertical height is supposed to be 150 times 0.12. Now, we have mass 900, and in gravity we know that mass times gravity times height equals to change, times the change in height equals to change in gravitational potential energy. So let me just write down these formulae, and we have 1/2 times mass times velocity squared. Okay, so we're going to have times 10, and then the change in height is going to be going from 0 all the way to 150 times 0.12, which by the way is 18 meters above and vertically, and that's the work done against resistance or by resistance, and that's what we're trying to find. So go ahead and use your calculator. 0.6750 plus 900 times 10 times 18, and that's equal to 162,000, plus the work done by resistance. Now if you add these two values together, you get 22750, plus the work done by resistance equals to 28800. So if you subtract each side, you get work done by resistance or against resistance be 65,250 joules. Okay. Question after this, however, says the car then travels along a straight horizontal road. There's a resistance to the motion of the car, and this is the resistance that's given to you. He says that the speed of the car is v meters per second, and the car travels at a constant speed with the engine working at a constant rate. However, it's 32 kilowatts instead. So he said find the speed. Now from the same car, part I is going to have a mass of 900. There is no drive force. The drive force is different because the power is changed. And so let's try to find the speed given now. Instead, it's again a car of 900 kilograms, and it's working at a power of 30,000 watts. So we know that power equals to work divided by time, but we also know that power equals to force times velocity, and that's another formula for power. And so if we know that it's moving at a constant speed, that means that the driving force must equal to the resisting force. And so we know that the resisting force equals to 1520 plus 4v. So there you go, you have the driving force in terms of velocity, and you want to find velocity, so you can just go ahead and write an equation in terms of velocity. And so 1520 plus 4 times v, and you can expand everything here. You get 1520 times v, 4v squared equals to 32,000, and then you could just solve a quadratic equation over here. 4v squared plus 1520v minus 32,000 equals to 0. So on your calculator, A is 4, 1520 is B, and negative 32000 C. And so velocity will equal to 20, or velocity equals to negative 400. However, I do not understand what will prompt the car to start moving backwards. It's going to be 20 meters per second. Okay. Question number 7 talks about a particle moving in a straight line with a velocity at time t seconds given by, and we got equations for velocity in terms of time. And we can see this is 4 different time intervals. Show that there is an instantaneous change in acceleration at time t equals 10. So an instantaneous change in acceleration at time equals 10. We know that acceleration equals to dv on dt, or the rate of change of velocity. And so if we differentiate velocity, we can go ahead and say 0.25 times 2, that's equal to 0.5 t minus 8 for the derivative. He says to show that there's an instantaneous change, so I can find so I can show that the acceleration before that, and I also know this is acceleration in part 2 when time between 10 and 20. However, between time 0 and 10, the acceleration again is a derivative, and in this case the derivative will equal to 0.5. Now let's place time equals 10 into this equation. So 0.5 times 10 minus 8 is equal to what? 0.5 times 10 is 5 minus 8 is going to be negative 3 meters per second squared. And so you can see there's an instantaneous change, because at the same second when the particle is supposed to be moving at an acceleration of 0.5, it actually has now an acceleration of negative 3 meters per second squared, and so there's an instantaneous change. Next we have B, which says find the total distance covered by P in interval 0 to 20. So it's important here to sketch, but another thing that's very important is for you to find the points of instantaneous rest when it comes to total distance. Total distance is different to displacement. Displacement can be found just by integration. However, displaced distance does not ignore, what's it called, points where like you were moving backwards and everything. Because if someone was to move like this, his displacement is just this over here, this distance over here from the origin. However, his distance is the distance that he covered from here to there, plus the distance that he covered from this point to this point. And at this point, we have instantaneous rest. At the point that we turn, we have instantaneous rest. So it's important that we know the points of instantaneous rest, such that we're able to calculate the distance from this point until the instantaneous rest, and then from the instantaneous rest to the different points that we have. So in order for us to find the instantaneous rest, we just make velocity equals to 0. So let's continue right here. 0 equals to 0.5 t. So here we're only at rest at 0 seconds. That's fine, we started from rest, but I'm not looking for this. I'm looking, let's say, for the next part, next interval, b equal to 0. Let's see what time is it at rest. Negative 8 and 60 time is equal to 20 and a time equals to 12. So we can see that it comes to rest at the very end. However, at what's it called, time equals 12, it turns around. So we know that at what's it called, for the journey, it was moving like this with a obviously acceleration, what's it called, constant acceleration. Then it comes to time equals 12, it turns around, and we know that overall, when it comes to turn around at the time of 20, we want to figure out how far it has traveled, obviously, but let's go ahead and see what we can calculate. So we know that between 0 to what's it called 10 seconds we can calculate displacement, but first distance equals to the integral of velocity with respect to time. So let's integrate the first section. 0.5 t squared divided by t2, and that's from 0 to 10 seconds. So there's no turning around here. We don't need to stop the limits at any different weird point. So let's go ahead and put in 10 squared, and that's going to equal to 25 meters. When you plug in the limits, you're going to get 25 meters covered in the first 10 seconds. However, between 10 and 12 seconds, we're going to continue moving forward in the same straight line, but after that, we're going to turn. So I would recommend integrating the second equation, 0.25 t squared minus 8t plus 60 with respect to time between the time 10 and 12, and so that's going to be between 10 to 12. 0.25 divided by 2 is going to be 0.125 divided by 3, excuse me, that's different. Okay, that's going to be 1 over 12, so let's move this. It's going to be 1 over 12 time cubed minus 4 times squared plus 60 times time, and if you plug in the limits this time, you're going to get 1 over 12 into 12 cubed minus 4 times 12 squared plus 60 times 12, and that's going to equal to 288. So that's the first limit, right? Minus, so between 10 and 12. Obviously, you need to show every step of substitution because that gives you marks. But here I'm going to get a quick calculation, right? Minus 4 times 10 squared plus 60 times 10, and that's going to be 850 over 3. What is going on? Okay, minus 850 over 3, which is 283. And so 288 minus the answer is going to be 14 over 3 meters. And so initially we covered 25 meters, and then we continued in the same straight line but with different acceleration, 14 over 3 meters, and then we turned around. Now this is what I'm interested in. Get the displacement. Let's go ahead and do this. Get the displacement between time 12 to time of 20, because from then on we do not switch our directions, and so displacement will equal to distance. So 1 over 12 times 20 cubed, minus 4 times 20 squared plus 60 times 20, and that's going to be 800 over 3 minus, at time of 12 seconds, we're going to get 188. 800 over 3 minus the answer is going to be a distance of negative 64 over 3. Pretty interesting, huh? Yeah, well, we do move in the opposite direction. That does make sense. However, okay, yeah, we do move in the opposite direction starting then. And so the distance from here to there, like we moved 25 meters, then we moved 14 over 3 meters, then we turned around and covered 64 over 3 meters. So the total distance is going to be 64 over 3 plus 14 over 3 plus, as we mentioned, 25 meters. And so if we add all these together, you're gonna get 25 over 3 meters. Actually, it is 51. Made the calculation mistake. So that's it. Thank you guys for watching. If this video was helpful, please make sure to like and subscribe and share it to someone who might want to check it out. Thank you again, and see you in the next one.